Hello class, today we are going to have a short lesson on the rates of reactions. In order to understand the rates of reactions, we first must define collision theory. Collision theory states that atoms must collide with sufficient energy and proper orientation in order for a reaction to occur. If we look at the reaction below, the reactants A and the compound BX must collide together in order to form a new compound AX plus B. In order for this to occur, when the molecules strike each other, they must strike each other with the correct orientation or direction. If they don't have the correct orientation, the bonds will not break and the products will not be formed. If we look at this first collision, A strikes B, and if we were to follow this, you potentially could end up with a product AB plus X. That is not the reaction we want to occur. So we do not have the correct orientation in this first collision. If we look at the second collision, A strikes X instead. By striking X, we are now in proximity, so that way a bond could form between X and A, and then the bond that was keeping X and B together will break. That will cause B to be ejected, and we'll end up with B plus AX. This is considered an effective collision. Orientation isn't everything. We still need enough energy for this reaction to occur. To help us understand this a little bit better, we need to look at the progress of a reaction over time. When reacting, substances briefly form an unstable transition state. In order to get to that transition state, we need activation energy. This is the energy that colliding particles need to form a transition state and then react. So when we say sufficient energy, we're really talking about the activation energy. We have to overcome the activation energy barrier in order to break bonds and form new ones. In this graph, which is referred to as a potential energy diagram or a reaction coordinate grid, you can see the progress of reaction over time and the amount of energy that goes into that reaction. Here, we start off with reactants that are higher in energy than the products. When the reactants have more energy than the products, or a higher potential energy, we know that this reaction will end up being exothermic. The energy given off by the reactants is referred to as delta H, which is the amount of heat. That is the difference in energy between reactants and products. If products are lower than the reactants, that means heat is given off or released. If we look at a different graph where products are higher than reactants, here are your products and your reactants, then the amount of energy, delta H, is absorbed by the reactants to form products, and that energy difference tells us this is endothermic, meaning heat is absorbed. When we're looking at the other variable here, EA, that is our activation energy. So every reaction has some activation energy it must overcome in order to get past the transition state, which is at the peak here, and then start to form products. If you don't have sufficient energy, then you won't make any products. Here's another graphic that depicts effective and ineffective collisions. In this particular reaction, NO2 is the goal. They want to form NO2 and O2. If it strikes in the first two ways, NO and O3 striking together, they will not form the molecules that they want, and we see that NO and O3 remain intact. This is the only possible way for an effective collision to occur, so that that OO bond breaks and an NO bond forms. There are 4 factors that affect reaction rate. The temperature, which we know is the average kinetic energy of our particles, affects reaction rate, and it's very similar to the idea of kinetic molecular theory. If we are at higher temperatures, the reaction will occur faster because there are more frequent collisions and therefore more high energy particles. They have enough energy to reach the activation energy and the transition state. If we increase the concentration, this also causes a faster reaction because there are more particles and therefore more frequent collisions. Particle size matters. If we have a smaller particle size, that means we have more surface area, which means there are more available areas for collisions to occur. Since there's more space for molecules to come in contact with each other, the reaction will occur faster. The last one is a catalyst. Catalyst causes a faster reaction by lowering the activation energy. By lowering the activation energy, that peak that we saw on that reaction coordinate diagram, it is easier to get to the transition state. So here is a good example of what it looks like when there is and when there is not a catalyst. The peak decreases in magnitude when there is a catalyst. Therefore, the only energy needed from here to here is much lower than the energy needed from here to here. Therefore, it is easier for the reaction to occur. I also have 2 videos at the end of your notes page, one dealing with enzymes and one from TED Ed. Please make sure you watch those and record some additional notes.